Everyone. Today we're wrapping up our unit on quadratics, and so we're really just kind of pulling together some odds and ends here. We've talked about a lot of the important things when it comes to quadratics, but probably time to get a good definition down for what it means to be a quadratic function. So a quadratic function is any function with a degree of 2, and that is just a fancy way, if you remember when we talked about degree last year, that is just a fancy way of saying the equation has an x squared in it. Okay, those are quadratic functions. These will always be parabolas. And then quadratic modeling is really the same idea as all the other types of modeling we've talked about so far. So we've talked about linear modeling, we've talked about exponential modeling. In general, modeling means we're going to write an equation to represent a real life situation. So today we're going to look at some different models that can be used for quadratic situations. Okay. And if you need to pause to finish writing down those definitions, you certainly may. So I've got general form of a quadratic, and I actually don't like that I use the word general here. This is considered to be standard form because, of course, in the last couple of lessons, we focused on the difference between standard form and vertex form. So this is standard form. You'll see that x squared sitting there. And I just want to take a minute to talk about some general properties of all quadratic functions. And I'm going to draw myself a parabola here. This is a generic parabola, okay, that would represent a quadratic, just so we can use it as we refer to all this stuff. So for domain, the domain of a quadratic function, no matter what, no matter where that parabola is located, is always going to be all real numbers because there's no restrictions on what I'm allowed to plug in for x here. And if I look at it on a graph, that graph is going to spread out forever left and right. Now, the maximum and minimum, we've got a couple of things to mention here. If the parabola is pointing upward, like this one is that I drew, it has a minimum value, okay? If the parabola is pointing downward, it has a maximum value, okay, because the vertex is at the top. So first off, I guess I would just mention that the minimum maximum is always located at the vertex. And then depending on which way the parabola is pointing, that's how you determine whether it's a minimum or a maximum. Now, you can tell which way the parabola is pointing from the equation, specifically the a value. So when a is positive, meaning a is greater than 0, the parabola points up. And in that case, we have a minimum value, okay, because when it points up, that vertex is at the bottom. When a is less than, or I'm sorry, not, a is greater than 0. Okay, a is less than 0 would be negative. Sorry, lost my train of thought there. When a is negative, the parabola is going to point down. And in this case, we're looking at a maximum. Okay, and we've talked a lot already about how to find where that vertex value is. So if you had to find the minimum or the maximum, you could find it by just calculating the vertex one way or another. So the range is going to depend on which one of these situations I'm living in. If I'm living in this situation where my parabola is pointing upwards, it's always going to be all real numbers greater than or equal to wherever that minimum value is. So everything from here up. If I'm looking in this situation, it's everything from here down. So I would say the range, let's see, when a is greater than 0, is all real numbers greater than or equal to the k value. So that's remember the vertex is h comma k. Okay, so looking at where that y value is located, that'd be this value here. It's all real numbers greater than or equal to that number. When a is less than or equal, or sorry, just less than 0, didn't mean the equal to there. When a is negative, that's really what I'm saying here. I don't know why that's not erasing for me. Sorry. When a is negative, it's all real numbers less than or equal to that k value, because then I'm living in this situation. So again, this is when we're pointing upward. This is when we're pointing downward. Okay. The vertex is always located at h comma k. And we've talked about two different ways to find that vertex value. We have, if it's written in this form, remember we have this formula, h equals negative b over 2a. And then you plug in h. This is just a review of the last couple of lessons. to find k. Okay, plug in h to the original equation. Or if the equation is written in vertex form, the h and the k are just kind of sitting there for you. So however you can find h and k, that's your vertex. X-intercepts can be found by doing a quadratic formula. And typically you're going to find that there's two x-intercepts. There are situations where you can have one or none for sure, but typically I would expect when you do the quadratic formula to walk out with two answers. Okay. And then the y-intercept is always the c value, and I'll show you why. Because the y-intercept is always where x is equal to 0. If you look at this equation, if I were to put a 0 here and a 0 here, essentially the whole first part of this equation would cancel out and you'd be left with just the c. So wherever that c value is, that's where your y-intercept of your parabola is going to be. I didn't draw either one of these to have a y-intercept showing, but c value will always give you your y-intercept. Okay, so let's do some examples here. So we've got 2x squared minus 9x plus 3. Find the x-intercepts and the y-intercepts. All right, so for the x-intercepts, my best bet, because this thing is written in standard form, I'm going to do quadratic formula. So I'm going to say x equals negative b, so that'd be positive 9, plus or minus square root of negative 9 squared, minus 4 times 2 times 3, all over 2a, so that's 2 times 2. I'm going to do just the piece that's underneath the square root right now. So negative 9 squared. Oh, sorry, you can't see that, can you? There we go. Negative 9 squared minus 4 times 2 times 3. And I get 57. So 9 plus or minus square root of 57 over 4. Now, square root of 57 is going to be an ugly number. And that's okay. We're going to just go ahead and make it an ugly number. So I'm going to do square root 57. And I'm going to get 7.55. So this is where I'm going to split and say it could be 9 plus 7.55 over 4. Or 9 minus 7.55 over 4. Okay. In my calculator, I'm going to do this in 2 steps. So 9 plus 7.55. Notice I'm hitting enter, and then I'm dividing by 4. So, and I'm going to feel okay about rounding this because I already rounded this number. So I'm going to just say this is approximately equal to 4.14. And then this guy is approximately equal to 0.36. And these are your x-intercepts. Okay, so what I just found right here were the location of my 2 x-intercepts. Now let's talk y-intercept. Y-intercept is actually a lot easier. My y-intercept is sitting right here for me. Okay, so my y-intercept is just that c value. Again, because the x-intercept is where I'm plugging a 0 in for, the y-intercept is where I'm plugging a 0 in for x. So if I plugged a 0 in for x, this first part of the equation would all cancel, and I'd be left with just the plus 3 on the end. Okay, so I'm going to go ahead and do these 2 questions, and then I want to graph this thing, and we'll just kind of check it together and make sure all of our answers check out. So this just says tell whether the parabola has a maximum or a minimum value. And remember that comes from the a value. So in this case, the a value out there in front of the x squared is 2. That's positive. And so that means my parabola is pointing up. And so if you can kind of visualize the parabola pointing upward, that means that this has a minimum value. Okay. And then when it says find the coordinates of the maximum minimum point, I just want to point out that when I ask that question, really what I'm asking for is the vertex. Now there's 2 different ways, excuse me, there's 2 different ways you could go here for finding the vertex. You could do completing the square and convert this thing into vertex form, or you could use the calculations to find h and k. I'm going to go through the calculations to find h and k. I think that'll be a little shorter in this case because these numbers are kind of ugly up here. So I'm going to say h is negative b over 2a, which in this case would be positive 9 over 2 times 2, so 9 over 4. And 9 over 4 is going to be 2.25. And then to find k, I'm going to take that 2.25 and plug it into my equation. So 2 times 2.25 squared minus 9 times 2.25 plus 3. And that gives me a k value of negative 7.125. And so I would say my minimum value is at 2.25, comma, negative 7.125. Okay, this would be my answer for that question. Okay, so now what I want to do, I'm going to use the tool, the online tool Desmos, which is an online graphing calculator, to graph this parabola. And I like Desmos even more than I like your graphing calculators because it does allow me to just click on the parabola and see the intercepts. There are ways that you can do it on your calculator, but it takes a few more commands than I think it probably should. So let's do this. Desmos. I'm going to just type in that equation. So 2x squared minus 9x plus 3. There's my parabola. And so just to remind you here, let's see if I can do this kind of split screen. I said a second ago that my intercept should be at 4.14 and 0.36. So here's one intercept at 4. Oh, that is not good. 0.114. Oh, because I put plus 3. Sorry. This should be a plus 3. Okay, there we go. That's 4.14. And there's 0.36. Okay, again, we rounded, so ours are a little off. But if I hover over those 4.14 and 0.36, okay, sorry about that little mix up there. And then when I look at the vertex, I'm expecting to see this number, 2.25 and negative 7.125. And there it is. Okay, also my y-intercept is listed for me here too at 0, 3. All right, which is where my y-intercept should be. So you could get this information straight from Desmos. Just realize you won't have Desmos to work with like on your chapter test or anything like that. So just make sure that you're able to do all of that mathematically, but Desmos is a great way to verify when you're done. Okay, next up we are going to talk about a very specific type of quadratic model, but it's very commonly used. It's actually an application from physics, and that is Newton's formula. You did a little bit with Newton's formula last year, but what Newton's formula is all about is projectiles. It's things being either thrown up into the air or being dropped from a certain height, and it gives the height of the object as a function of time. So based on how long it's been since you let go of whatever the object is, this is the equation that kind of models that. Okay, so just to kind of lay a couple of things out here, and I'm going to grab a different colored pen here. The h and the t are like your x and your y, so that's where we're filling in height and time. The g value is acceleration due to gravity. I'm just going to write gravity here. And this is actually a constant value as long as you're on planet Earth. Now, it's constant, but it does change depending on whether you're measuring in feet or meters. It's just a conversion there. So if we're measuring in feet, the value of g is always going to be 32. If we're measuring in meters, the value of g is always going to be 9.8. And you do need to know those two numbers that depending on the situation, you'll have to plug in either a 32 or a 9.8. Like I said, we're leaving the t squared alone. These are the two values that are actually going to be given to you in the problems. This is the initial velocity. and this is the initial height. So really you are just filling in numbers for G, V sub 0, and H sub 0. And then what you'll be looking at is a quadratic equation that uses H and T instead of X and Y. So let's dig into that with this first example. A projectile is shot from a tower 10 feet high with an upward velocity of 100 feet per second. So this 10 feet high, that's my initial height. That's H sub 0. Upward velocity of 100 feet per second, that is my V sub 0. That's my initial velocity. And then because it's being measured in feet, I know that my G value is going to be 32. So if I plug that in, I have this, -1/2 times 32 t squared plus my initial velocity was 100 plus my initial height was 10. And the only thing I can do with this equation that would really clean this up is put together the -1/2 and the 32. So this is the equation I want to work with. -16t squared plus 100t plus 10. Okay, so these next two questions, we really need to think about what this parabola is going to look like. Remember, this model is an object being thrown up into the air. So when I graph this, it's going to look something like this. It's going to start at 10 feet up. So this is a distance of 10 feet. It's going to go up and it's going to come back down. So when I ask, and this is what the parabola should look like every time. And if you notice, that's a -a value. So that's why you're always looking at an upside down parabola. So how long will the projectile be in the air? I'm really looking for the time at this spot right here. This is where it's hitting the ground. And so I want to know how much time is that. I could do this problem with quadratic formula, and I'm going to actually show you how to do it on the calculator, but I want you to know if you're not good with the calculator or if you forget what to do with the calculator, you could do quadratic formula here and you would find this answer. Okay, that's mathematically how you would find it. And then, for example, what is the object's maximum height? Well, here's the maximum, right? And that maximum is going to be there's going to be a t value for time, and then there's going to be an h value for height. So when I look at this value, or sorry, t comes first. T comma h, okay? This is the maximum height that I'm looking for. So really I'm looking for like the k value from the vertex. So anytime I'm talking about the maximum, I'm talking about the vertex of the parabola. And you just have to decide whether it's h or k from the vertex that you need. So if you look back up at that example 1 that we did, really this just corresponds with what we did in example 1. Okay, the math we did in example 1 would correspond exactly with these questions. Like I said, I'm going to go through how to do this on your calculator, but if you wanted to do it mathematically, you could just follow basically the same process we did up there. So in my calculator, I'm going to go to y equals, and I'm going to graph this equation that I came up with. So I'm going to graph -16 x squared plus 100x plus 10. Now, this is the big trick with these parabolas, and I don't know how I have my window set, but I'm going to go ahead and hit graph. And you'll notice I probably won't see much of anything at all. Okay, I see a little bit. But my window is not set in a way that's going to give me this picture, right? First of all, I don't care about anything negative. So essentially, I don't care about any of these parts because I can't have negative height and I can't have negative time. So I'm going to go to my window button, and this is the part that tends to bother people. We're going to adjust our window manually here. So on my x-axis, I don't care about anything negative, right? So my smallest x value I need is 0. And then I want to think about what's the highest x value I might need. How much time could this possibly take? If you throw something up into the air and wait for it to come back down, think about how long it could possibly take. And I mean, I think 10 seconds is plenty. I could probably even shrink that down some, but I'm going to leave it at 10 for right now because I'm thinking about what that picture looked like a second ago. And then let's look at that y value. That's talking about the height. That's talking about this. Again, I don't need anything negative, so the smallest y value I need is 0. The Y max is where it sometimes gets tricky to guess because there's not really a value in the problem that tells me how high this thing could possibly go. So I am literally just taking a stab in the dark here. I know from what we looked at just a second ago that 10 was not high enough to see the top of my parabola. So I'm going to make a guess at 50. Maybe it's going to go 50 feet up in the air. Okay. And I'm going to hit graph and see what happens. Okay. So at 50 feet, I still can't see the top of this parabola. Now here's what tends to happen in this situation when I do this with students. I say to them, okay, we need to guess something bigger than 50. And they say, okay, how about 60? Okay, how about 65? Don't make little guesses like that. It's okay if you guess something that's too big. All right, I would rather you take a big guess than a small guess and have to do it over and over again. So I'm going to change my 50 to 200. I'm going to just, and again, I didn't calculate that at all. I am just taking a guess here. I just want to see how high I need to make this so that I can see the top of the parabola. Hit graph, and that is a beautiful picture. What I need to be able to see is where it hits the x-axis and where the top of the parabola is. So you may have chosen something different for your window and still been able to see those two things, and that's okay. But I think the hardest part about this is getting that window set correctly, and it is just a little bit of trial and error. Okay, so if I want to find, let's see, the first thing was to find this value here. So I'm looking for this. I'm going to go to the calc menu, which is up above trace. So I'm going to hit second calc. And what I'm really looking for here is the zeros. So I'm going to choose that. Okay. What my calculator is asking me to do is give a left boundary and a right boundary for that point that I'm trying to find. So what I need to do is tell my calculator, I'm going to set my boundaries here, somewhere to the left of the star, and here, somewhere to the right of the star, so that my calculator knows to look in between those two things for that place where it crosses the x-axis. Now, where my cursor is at right now is actually would work as a left boundary, right? It really doesn't matter as long as it's somewhere to the left. I'm going to move it so it's just a little bit closer, but it really wouldn't matter even if I had done it where I had it before. I'm going to hit enter, and notice that when I hit enter, I got this little triangle here that's marking where this first line is going to be, and now it's asking me for the right boundary. So I'm going to move to the right, and it's going to move off the screen where I can't see the cursor, but my right boundary should be somewhere after the parabola has dipped below the x-axis, which means my y values should turn negative. So you'll notice that my y values have turned negative. I can't see my cursor, but I know that it's somewhere beyond that star, and so that's a good enough place for me. So I'm going to hit enter. And then one more time, your calculator says guess. Your calculator is just very insecure. This is your calculator saying, do you want me to give you the answer now? And you're going to say yes. So you're going to hit enter one more time. Okay. And notice that it gives me that my 0 is located at 6.35. So that answers this question. How long will it be in the air? About 6.35 seconds. And again, that's the same thing we would have found if we had done the quadratic formula. Okay, now let's talk about that maximum height. So I'm going to do a similar thing here. I'm going to go to the calc menu, which is up above trace, but this time I want to look for the maximum. And your calculator needs you to do something similar to what you did before. It needs a left boundary and a right boundary. But remember, now I'm not talking about the 0. Now I'm talking about the maximum. So I have a left boundary here and a right boundary here. I want to go somewhere to the left of the vertex and somewhere to the right of the vertex. And if you think about where my cursor is right now, my cursor is somewhere down here, right? It's below the x-axis. So I need to move back up this way to the left. There it is. And I want to go to the left of that vertex point. So just somewhere past the peak there. I'm going to hit enter. You'll notice that little triangle pop up. That's kind of marking the location of this first line. Then I'm going to move somewhere to the right. So I'm going to move somewhere to the right of the vertex. Again, that's giving me this line here. When it says guess, hit enter one more time. Now, that's giving you the coordinates of that vertex. So we know that the coordinates of the vertex are 3.125, comma 166.25. The question is, which one of those do I actually want? And it depends on what the question's asking. This one's asking for the height. What is the maximum height? Remember, this is time and this is height. So the height would be 166.25. If the question had said, when will it reach the maximum height, then I'd be looking at the 3.125. Okay. And again, if you are not comfortable with those steps we just took on the calculator, you could always fall back with quadratic formula and finding the vertex. Okay, one more quick thing to cover, and this should be familiar territory for you. So I don't know why we'd ever take the time to do a quadratic model here for a doodle, but a student was doodling and drew this pattern of dots, okay? And it says, write a set of ordered pairs to relate the order of the image to the number of dots in the image. So what I mean by that is I'm going to call this image 1. I'm going to call this image 2, 3, and 4. And then I want to say how many dots are in each picture. So this one has 1 dot. This one has 5. This is 3, 4, 5, 6, 7, 8, 9, 10, 13. And this is... I think this is 25. Hope that's 25. Okay, yeah, I think 25. So my set of ordered pairs would be this. 1, 1, 2, 5, 3, 13, and 4, 25. Okay. I will just tell you, I'm going to save you the pain of having to like draw this graph here. But the shape that you should see when you graph these points is a parabola, okay? And I know that by looking at this, because notice that this thing is growing like a square, right? It's growing in 2 directions. It's growing this way and it's growing this way each time. That's a quadratic pattern, right? Where you're growing by a factor of x squared, okay? So this will form a parabola. Like I said, you could graph this in your calculator and see a scatter plot, but you should see that these points form a parabola. What I really want to get into is this piece, find a quadratic model linking x and y. So let's think about this. We have coordinates, right? We want to do some modeling. We've been in this situation before. We did linear modeling. We did exponential modeling. Now we're going to do the exact same thing, but with quadratic modeling. So I'm going to go Stat and Edit, clear my lists. We've been down this road before, right? Okay. In L1, I'm going to put my image numbers. So I'm just going to do 1, 2, 3, and 4. In L2, I'm going to put the number of dots. So that's 1, 5, 13, and 25. Okay. Now remember, modeling means we're doing some sort of regression. So I'm going to go to Stat and Calc. Now I'm not doing linear regression this time, and I'm not doing exponential regression. I'm doing this number 5, where it says quadratic regression. Enter. On this calculator, I'm just hitting enter. You may have to go down and choose calculate. Okay. And notice it gives me a quadratic, ax squared plus bx plus c, and it gives me an a, b, and a c value. So my quadratic model looks like this. 2x squared minus 2x plus 1.